So electronegativity, which I think there we go. We need to say what it is first before we talk about how it changes. Electronegativity can be defined as the ability of an atom in a molecule to attract electrons to itself. So this is a little bit like, how cool is the house that this little boy comes from? Is it the really cool house with all the fun toys, or is it the boring house? Maybe mom's kind of cranky even. It's just not very attractive, right? So electronegativity is a measure of the ability of an atom to attract electrons. So we talked a little bit about bond energy being the energy required to break a bond. If we have a molecule HX, hydrogen and some other element, they figure out the relative electronegativities of these, and it's all relative because it's not something that can be measured absolutely. What do you call zero? They determine by comparing the measured bond energies to the expected bond energies. And if that doesn't make sense, it doesn't really matter that much. What matters is that we understand the idea of electronegativity and that we can use the periodic table to compare elements. So on the periodic table, electronegativity generally increases as you go across the period, so from left to right, and it decreases as you go down. And we'll look at that on a periodic table on the next slide. The range of electronegativity values is from 4 for the highest down to 0.7 for the lowest. And they just, the guy who came up with this decided that 4 was going to be the highest. A little bit like they decided a grade point average was 4. So here's a periodic table. And what we see is as we go across, the electronegativity values increase. So on this periodic table, we're given the electronegativities instead of the molar masses. And if we go down any of these groups, it goes down. I think the best way to remember this, though, is that fluorine is the awesomest. So fluorine is the most electronegative. And the closer you are to fluorine, the more awesome you are, the more electronegative you are. So as we go across in a row, a period, as you get closer to fluorine, the electronegativity increases. When you go down, you're going away from fluorine, and so it decreases. So we need to know that and be able to compare different electronegativities. What's missing from this periodic table? There's some elements over here, right? Those are the noble gases. The noble gases don't form compounds. They form a couple, but very, very few compounds. And so electronegativity for the noble gases is just not even worth talking about because they really just don't form bonds. So that's why they get left off of this table. So if lithium and fluorine react, which has more attraction for an electron? So let's just sketch out periodic table here. There's fluorine and lithium is way over here. Which is more attractive to an electron? Fluorine. Why? It's more electronegative. So fluorine is more attractive because it's more electronegative. So if we had a bond between fluorine and iodine, which would have more attraction? So, oops, what did I do? Did not mean to do that. Fluorine and iodine, let's just look at this end of the periodic table where they are. Fluorine's up at the top, and iodine is further down, right? So fluorine has more attraction, again, because it's more electronegative. We're not going to explain the trend. What is the trend across the row? As you go across the row in the periodic table, does electronegativity go up or down? It increases. And I think the simplest way, like I said, is to remember that fluorine is the awesomest. And so as you're going across, it's going up because you're getting closer to fluorine. What about as you go down in a group? It decreases because you're going away from fluorine. So I'm going to put down instead of decreases because it's a shorter word. So we mentioned what a polar bond is. The polarity of the bond is going to depend on the difference between the electronegativity values. So here we have an illustration of a covalent bond between two atoms that have identical electronegativities. If the atoms are the same element, then they must have the same electronegativity. And so that's what I want you to be able to recognize. If this is two fluorine atoms or two hydrogen atoms, two of the same, two fluorines or two chlorines, two of the same, then it's nonpolar because there's equal attraction. In a polar covalent bond, like this one in the middle, this atom has a higher electronegativity. It's more attractive to the electrons. There's more cool stuff at this house, and so the little boys play over here more often than they play over there. So here we have, sorry, I blanked out there. Here we have the more electronegative element and the less electronegative element. There are pairs of elements that are different elements, and yet they have the same electronegativity. We're not going to worry about those. We're going to keep it simple and say if the elements are different, then it's going to be a polar covalent bond, if it is a covalent bond. And then at the other extreme we have the ionic bond with no electron sharing, and this happens between a metal and a nonmetal. If there's a metal involved, I wrote those in the wrong place. If there's a metal involved, this is the metal, sorry. If there's a metal involved, it's going to be ionic, because metals don't share. They just don't. This polar covalent bond is two nonmetals, not the same element. So this might be hydrogen and chlorine. So if you have two nonmetals that are the same, that's going to be a covalent bond. We sometimes call that a nonpolar covalent bond. If we have two nonmetals, but they're different, we're just going to assume that it's a polar covalent bond. There's unequal sharing. If we've got a metal and a nonmetal involved, the metal's just going to give an electron, or more than one, to the nonmetal, and it's going to be an ionic bond. There's no real hard line between these. It's a continuum. And so we're not going to worry about the fuzzy area in between. We're just going to look at the one end and the other end and right in the middle. Any questions? So here we have an illustration of the hydrogen atom again. And when the two hydrogen atoms get together, it's a lower energy state and they form a bond. And because these two atoms are identical, they're going to share those electrons equally. Would this be polar or nonpolar? Is there a different end? Is one end different than the other? No. So this is nonpolar. That's a nonpolar bond. So arrange the following bonds from most to least polar. So here in this first one, these questions are a little hard to get used to looking at even. So for A, we're comparing nitrogen with bonded to fluorine, oxygen bonded to fluorine, and carbon bonded to fluorine. The more polar bond is going to have a larger difference between the two elements. And we could look at the table that had all the electronegativities and calculate the difference, but that's too much fussing around. So what we're going to do is we're just going to look at a regular periodic table and identify all of these have fluorine in common. The most polar will be fluorine and the one that's farthest away from it on the periodic table. So these guys are all in the same period. Oh, interesting. Didn't mean to do that. So here's fluorine and oxygen and nitrogen and carbon.
So most polar is like polar opposites? Like
Right. The most different. Most polar means the ends are the most different. And so it corresponds to, generally, them being farther apart on the periodic table. Fluorine and oxygen, being right next to each other, are going to have electronegativities that are closer than fluorine and carbon. Because as we go across, electronegativity increases. Because oxygen is closer to fluorine, its electronegativity must be closer to fluorine's electronegativity. So the most polar bond will be between carbon and fluorine. And the least polar will be between oxygen and fluorine. And it says from most to least polar. So the oxygen, fluorine, nope, backwards. Carbon, fluorine is most polar. And then next is what? The nitrogen, and then the oxygen. You see how that works? Once you see the pattern, it's really not that hard. These two are closer together. So there's less difference between them. They are less polar in a bond. So let's look at the letter B. CFNOSIF. Well, we need a little bit more in our periodic table, don't we? Si is here under carbon. So now we're comparing carbon to fluorine, nitrogen to oxygen, and silicon to fluorine. So if we were drawing lines, carbon, fluorine, well, that doesn't work very well. Let's use these red arrows. There's carbon, fluorine, there's nitrogen, oxygen, and here's silicon, fluorine. Which arrow's longer? The silicon, fluorine. This is farther from fluorine in the periodic table. They are more different from each other. It's more polar. So SIF is the most polar. Which one is the next most polar? Which one's the next longest? CF. And which one's the shortest? NO. These two are the closest. They are the most similar. Because two things that are identical would be nonpolar. Two things that are very, very different are going to be polar. An ionic bond really is just an extreme of the polar covalent bond. The one house was so awesome compared to the other that the kid left that family and joins the other family. I know, weird. Okay, let's look at this one. Chlorine, chlorine, boron, chlorine, sulfur, chlorine. We need at least a piece of periodic table here. Boron is over here. C-N-O, and Cl is down here. What else do we need in there? Sulfur. Sulfur's over here. So we're comparing boron chlorine, sulfur chlorine, and then chlorine with itself. Chlorine bond, is that going to be polar at all? No, that's going to be nonpolar. So the least polar is going to be the chlorine-chlorine bond. Which one's the most polar? The furthest distance on the periodic table. The boron chlorine, right? And then in the middle will be sulfur and chlorine. Does that make sense? So the farther apart the two nonmetals are on the periodic table, the more polar the bond is. That is a generalization, but it works good enough for this class. Okay? Mm-hmm.
Let's say chlorine versus oxygen versus chlorine and chlorine.
That's a good question. Let's see what I can do here. Chlorine is right here. And the question is, how would you compare an oxygen fluorine with a fluorine chlorine? I wouldn't ask you to do that. Because using this generalization, you'd say, well, they're the same polarity. And actually they are pretty close, if not exactly the same in polarity. But I couldn't really ask you which one is more or less. So I'll only ask you a question like this where the differences in distance on the periodic table are different, actually, not the same. Any other questions? Which of these would be the least polar and yet still be considered a polar covalent bond? Well, let's look at these one at a time. Magnesium and oxygen. Is that a covalent bond? No. This is an ionic bond because magnesium is a metal. So that one's out. What about this one? OO. Is that polar?
No, it's not.
No, not polar at all. So then we've eliminated two of the choices. We're looking for the one that's the least polar and yet still a polar covalent bond. So we want to find the pair that is closest together on the periodic table. Carbon oxygen, nitrogen oxygen, silicon oxygen. So it's going to be the nitrogen oxygen, right? Because they're right next to each other. Carbon and oxygen are separated by nitrogen, and silicon's even farther away.